All right, so Jacob says that we're going to box in to find our horizontal asymptote. We are gonna box in the highest power of x. Now, be careful. What is the highest power of x in this problem? X squared. I have one x squared on the top, but I don't have an x squared in the bottom. So what do? Who remembers from yesterday? What do? Stick a 0 in. Now, this is trouble, folks, because when I box in the x squareds, basically I have 1 over 0. And what do I know about having a 0 in the denominator? It's not allowed. So this is no horizontal asymptote. You cannot have something over 0. And that's what we have. So there would be no horizontal asymptote in this problem. That's different than what happened yesterday. Remember yesterday it was 0x squared over 1x squared? You see the difference? That's 0. When that happens, it's 0. But when this happens, it's none. No horizontal asymptote. Now, is there a vertical asymptote? Yes. Where is the vertical asymptote? At x equals 2. Because x minus 2 cannot be 0, so x can't be 2. And wherever there's a cannot be, there's a vertical asymptote. All right, how about the next one? What do you think we ought to do with this guy? Same thing in terms of the horizontal asymptote. So he says for my horizontal, the biggest power is x cubed. But I don't have one on the bottom, so I'll go ahead and stick one in there. But don't I have the same situation? I can't have 3 over 0. That is never allowed. So where's the horizontal asymptote? There isn't one. There isn't one. Not every picture is going to have a horizontal asymptote. And this is when you don't have one, when you got that situation. All right, what about verticals? Jacob?
Factor.
I'm going to factor. And my top doesn't factor. Please, that is not a quadratic. That's not an x squared, that's an x cubed. Don't factor that. Don't try to factor that. You can't. But you can factor the bottom. And how does the bottom factor? Minus 2. Aren't they both minus? When would it be x minus 2, x plus 2? Declan?
Positive and negative.
Exactly. That would be the difference of squares when you do x plus 2, x minus 2. This has a middle term, so this is going to be x minus 2, x minus 2. But since they're the same, there's really only going to be one asymptote, right? And where is it? X is 2, just like this one over here. So there's no horizontal. I didn't even discuss holes on these two problems. Why?
No cancels.
Because nothing canceled. The only way you get a hole from yesterday, remember, is you have to, when you factor, you have to be able to cancel. Well, shoot, I can't even factor that or that, so there's no way I'm going to cancel. If I could, I would have a hole. All right, we're moving on to something different, completely different. So before we do that, let's touch base. How do you find vertical asymptotes? Where do the vertical asymptotes come from? The denominator?
Or the radical.
No, vertical asymptotes are only the denominator. You're thinking domain.
Oh, yeah.
And they're very closely tied together. But in terms of asymptotes, it's the denominator. Where do horizontal asymptotes come from?
The highest power.
Highest power, boxing it in, and then comparing 3 over 0, or whatever. Okay, well, back a long time ago when we handed out all this stuff for this chapter, you received a BFF sheet. It's a little tiny packet that looks like this. And it says, make the BFF your BFF.
The second you get out of this class, you check your phone. See it all.
Yeah, it should only be. You got a couple of them.
Yes, nice.
Where did you see that? On my people?
My book. 3 people texted me and I looked it up.
Okay? Now, there is a lot on this paper. We use this same format for academic pre-cal and honors pre-cal. There is more on here than you are responsible for. Okay? So I'm gonna tell you what you're responsible for, and we're gonna go through it today. This is gonna involve flashcards and memorization. Okay? You are responsible for knowing the name of the function, and on the paper, they give you the name. So if you look at the very first one, it says the identity function. That's the name. And then the next one says the squaring function. That's the name. The names are already written on the sheet. You're responsible for the equation. I'm gonna give you that. And you're responsible for the graph. I'm gonna give you that. And when I say graph, I mean just, you know, you're just gonna sketch it on the grid here. It's nothing like precise, plotting a bunch of points. If there are important points, I want you to know, I will put them on my graph and you will know them. But there aren't very many where we have that. All right, everybody ready? So the very first one is called the identity function. The identity function is also called, and I don't care which name you use, but it's also called the linear function. Its equation is y equals x. So right on the paper, they have room for you. See where it says y equals? See where it says that? You're gonna fill in y equals x. That's the equation, the identity. And it looks like this. It's that perfect diagonal through the origin. The first of your basic family of functions is the identity. The identity is a line, so it's called linear, through the origin. Got it? She's making flashcards right now. What a novel idea. Okay. The squaring function. The squaring function is y equals x squared. Shouldn't be too hard for you to remember that one. Anybody know the shape of the squaring function? It is. It's a parabola, vertex here at the origin, opening up just like that. So here is the name, here is the equation, here is the picture. That's what you need to know. So all the rest of this stuff over here, I don't want you worrying about any of those words. You're gonna memorize the shape, the name, and the equation. All right, then we've got the cubing function. Any guess what the equation of the cubing function is?
Y equals x cubed.
You got it. See, this ain't gonna be so hard. And the shape of the cubing function, you may or may not be familiar with. It's kind of a squiggly line through the origin. That's the cubing function. So do your best to sketch this. Okay, page 1 done. we have the reciprocal function. And the reciprocal function is y equals 1 over x. That should be easy for you to remember, because if I say what's the reciprocal of 3, don't you say 1 over 3? The graph of the reciprocal function is a little bit crazy. It has asymptotes at x equals 0 and y equals 0. And then it is in quadrant 1 and 3. So what I drew in blue is what you need to draw. So you label your asymptotes, x equals 0 and y equals 0, and then you sketch in your curve. That's called the reciprocal function. What is going to happen, not next class, but the one after that, we'll have a BFF quiz. And I will draw some pictures, and you'll have to tell me what the name of that function is. Or I'll give you an equation, and you'll have to write, draw the picture. So we need to be able to do all 12 of these. There's 12 of them. Okay. What's next? Square root. Okay. You might imagine that the square root function is y equals square root of x. Sort of logical, y equals square root of x. And the picture starts here at the origin and kind of goes out like this. So it's kind of like a sideways parabola, but it's only the top half of it. That's the square root function picture. Everybody okay? All right, next we have the exponential. Now, the exponential is one that you will have to put a point, a special point on your picture. So I want you to put a point at 0, 1. So this is the exponential. And its equation is y equals e to the x. Y equals e to the x. Can everybody see that? It's behind the TV. You guys see it? Y equals e to the x. All right, so you've got a point at 0, 1. And then I want you to draw an asymptote here at y equals 0. And then I want you to draw this. Through that point. So out here on the left, it's coming down and getting closer and closer and closer. But here on the right, it is shooting up into space. Sometimes in science class or even on the news, you might hear people talking about exponential growth. This is exponential growth. It just shoots up into space. But back here, it gets little tiny and gets closer and closer to the line. That's your picture for e to the x, exponential. Okay? All right. Now we have the natural logarithm function. Now, I certainly don't care if you just want to call this the logarithm function. I'm okay with that. We don't need the word natural in there, because this is the picture for any logarithm, not just the base E logarithms. It's any logarithm. If you want to say natural log, I'm fine with that. If you just want to say logarithm, I'm fine with that. The equation is y equals ln x. That is an L, not a 1. It's ln, natural logarithm. Okay, ln x. That's your equation. Eli? You sure? That's an ln. Please don't say 1n. It's ln. And the picture, this is another one you have to have some points. I want you to put a point at 1, 0. And I want you to put an asymptote at x equals 0, so a vertical asymptote at x equals 0. And then kind of like that one, it follows this line up, and then it shoots out like this. So the exponential and the logarithm have a lot in common. They're kind of sideways of each other. So it follows this asymptote up, and then it just kind of shoots out. That's your logarithm. You okay with that? All right, now we've got the sine and the cosine. I'm not gonna be picky at all about this picture, with one exception. The sine, the equation is, it looks like sin, but it's sine. This is said sine x. The name of the function is sine, S-I-N-E. The equation is y equals sin x. Cosine is the same thing, only its abbreviation is COSX, COS, cosine. Now, the little grid on here is so tiny. This is gonna be hard to grasp. So what I want you to do is, we're gonna change the scale on your picture. So instead of having the first block be 1, because that's just too squished up, I want you to count up some blocks and call that 1. So I don't care how many blocks you go up, but stretch it out a little bit. This is gonna be 1. So on my graph, if I counted 4 blocks, it's like 0.25, 0.5, 0.75, and 1. You know what I mean, changing the scale? I just want you to do that so it opens up your picture. For the sine, I want you to start at the origin. And I want you to draw a hill all the way up to wherever you said 1 was. I want you to draw a hill. Then I want you to draw a valley all the way down to where you said -1 was. And put an arrow on the end. So you're gonna draw a hill and a valley. Then you're gonna do exactly the same thing backwards. So you're gonna draw a valley and a hill. This is your sine curve. Your sine curve is simply a wave. It's like a sound wave in physics. It's just a wave. It just goes up and down, up and down, up and down forever. It goes, its height is 1. This is 1 unit. And its depth is also 1 unit. That's a sine picture. Now, cosine, I want you to do exactly the same thing. Its setup is exactly the same. The difference is, remember how sine, I had you start at the origin? Cosine actually starts up here at 1. Its hills and valleys look like this. But it is exactly the same shape. It is hills and valleys. It's exactly the same shape. Sine and cosine are identical in everything except position. You need to keep them straight. So being the weirdo that I am, I'm going to share with you how I keep them straight. It's up to you. I don't care as long as you keep them straight. I'm a good Catholic girl. I remember original sin, sine goes through the origin. Original sin, sine, origin. That's how I remember. I don't care how you remember, but you gotta keep them straight. So when I say graph a cosine, this is what you graph. And it doesn't have to be perfect, but I better see a point up here. Right, hills and valleys. Got it? That's your sine and cosine. All right, we're almost done. We only have 3 more to go. We have absolute value, which is an easy one. Absolute value, the equation is y equals absolute value x. And the graph is a v from the origin. So I remember value v, value v. That's your absolute absolute value graph. Which one of your other ones that we've already done does this one kind of look like? The squaring.
function.
The difference is the squaring is a U shape and the absolute value is a V shape. So you want to make sure when you draw those two that you draw them different from each other. All right, next is my absolute least favorite of the BFFs. I hate to say it. Sometimes it's written, it's called the greatest integer function, that's its name. Sometimes it's written literally INTX, and sometimes it's written with a bracket, X, just one number in there, X in there. Either of those notations is fine with me. On the calculator, it's this. In your textbook, it's this. Either one's fine. And here's why I hate it. All right, I want you to put a solid dot at the origin. I want you to go over one block and put an open dot. So you actually draw that line in and put an open dot. Then I want you to come up one, right above your open dot, and put a solid dot. You go over one again. And then count up one, solid dot, over one. This is your greatest integer function. It is sometimes referred to as a step function. Does that word kind of make sense when you look at the picture? It's a step function. It goes up by steps. Now, when I'm grading your paper, what I will look for is, do you have a solid dot at the origin? And is your open dot to the right of it? That's what has to happen. The solid and open dots have to be in this order. So solid going over to open. Solid going over to open. And the origin has to have a solid dot. Any question about that? You good? All right, and then the last one. This is the tough equation. Most of the equations are pretty easy. This is a tough one. This is called the logistic function. And the logistic function has an equation like this. And it has a picture. Any question? That's a tough equation.
Is that a 1 or a L?
That's a 1. These are ones. They're both ones. The only L is in the logarithm. Put an asymptote at 0. Now, we need an asymptote at 1, but again, since your grid is so small, count up a few and just label it 1. Just go up somewhere and put another asymptote, and that's 1. Because the whole picture is in between 0 and 1. And it looks like this. It's the same kind of squiggly line that we had for our cubing function, except it's sideways. That's the logistic function. Okay? Now, some of you are already working on flashcards, and that's perfect. I want everybody to have a set of flashcards. It can be on regular paper, to tear up a piece of paper. It can be on note cards. It can be however you want, but I want everybody to have a set of note cards. And I'm gonna give you a grade for it, okay? So make a set of note cards. And I don't care how you structure it. There's 3 things you need to know. So 2 things are gonna go on one side and the other one's gonna go on the other side. So maybe you draw the graph on one side and then the back has the equation and the name. Or you put the name on one side and the graph and the equation. I don't care how you do your flashcards. but I want you to have some flashcards, okay? Because there will be some times when I will let you use your flashcards. And if you don't have any, then you don't have any, and you'll be on your own, okay?
You said the quiz is gonna be a picture of the graph and then.
Oh no, we'll practice. The quiz is gonna be all three. So I might give you the equation and ask you a question. I might give you the picture, ask you a question. We'll practice though. But your first task is not to worry about that. Your first task is to get your flashcards made. And start memorizing those things, right? Use your flashcards. Sometimes parents wanna know, how can I help my kid? I don't know anything about pre-calculus. They can help you with these flashcards. Okay? All right, so now we're gonna answer some questions about the flashcards. So, if you have your textbook pages that I gave you, get them out. We don't have much time, so if you don't have them, you just have to listen. But I'm going to page 113, and I'm looking at number 19. Number 19 says, find the 4 functions that are odd. My goodness, what does odd mean?
That don't have like an actual.
Well, we can certainly, you're coming up with a good plan, Scout. I love your creativity.
They don't have like I don't know. They're like not on center.
In function land, odd means symmetric about the origin. Origin, odd. Symmetric about the origin. Now, what does that mean? Well, let me draw one for you that is. The cubing function is odd. Because if I took this and folded it across the origin, this would turn into this. They're the same picture, just reflected across the origin. So look at your picture. So one of them is this one. Which one is this? This is the cubing? Okay, we have to find 3 more. Look at your pictures and see if you see any more that are reflections, that, you know, that what's in quadrant 1 is the same as what's in quadrant 3.
Identity.
Identity, absolutely. The identity, or remember, you can call that linear if you prefer. Sometimes if we use the word linear, it reminds us it's a line, but I don't care, they're both fine. Perfect. Any others? Sine. That's a tough one. You got the hard one. The sine curve is definitely odd. Very, very good. The sine curve. And what's the last one?
Greatest
No. I'm going to talk about that, Scout. That one's tricky. I heard it back here, I think. Reciprocal. The reciprocal function. Yep, the reciprocal function. So these are the ones that are odd. Now, Scout is thinking, which is awesome. She said, Mrs. Ford, what about the greatest integer? Now, the problem with the greatest integer is, if I flip this, these bars would have to be going the other way. So now the opens are to the right of the closed. When I flipped it, they would have to be to the left of the closed. And they're not.
But wouldn't isn't the still filled in one? Isn't that still like?
Okay, this would have to map onto this,
Okay.
and it doesn't. So that's a no. That's a no. It's very, I get it, but it's a no. These are the 4 right here, odd functions. Perfect. Next one. The 6 functions that are increasing on their entire domain. Now, what that means is, right here's an example. There's 6 of them. This is one. As I draw this from left to right, which direction is my pencil going as I draw from left to right? Up, that's increasing. So this whole picture, now, don't get confused. I know there's an arrow going down like this, but to follow that arrow, I would have to be moving right to left, and I never do. I never do. When I have a conversation about increasing, it's always left to right. So left to right, my pencil's going up, so that's one. What about this guy?
Yes.
Yes. Alright, so these two, there's 6 altogether, we got 2 of them right here. Is this one going up all the time?
No.
No, is it going up sometimes?
Yes.
But it's also going down, so I'm gonna erase that, he's not one of our 6.
Absolute value.
What about this one?
No.
Nope, that one's not either, so I'm gonna erase him too. You gotta hurry up, this last thing we'll do, let's see if we can come up with the other 4 that are only going up.
The absolute value.
Exponential?
Oh, I love the exponential, because the exponential's the one that looks like this. It goes up the whole time, very good. Square root goes up the whole time, perfect. That's the square root function.
Logarithm?
The logarithm function has an asymptote here, remember? It looks like this.
Absolute
It's a
value?
logarithm function. By the way, please don't abbreviate your logarithm function, LOG, because we also have the logistic function, right? So we have to write those words out. You have to write logarithm, and if you misspell it, but I can tell what it is, I'm fine. But don't say LOG, because I don't know which one you mean.
Absolute value.
Absolute value, yeah.
Absolute value, be careful. When I draw absolute value, which way is my pencil going?
It's going.
That's not that one. Logistic. The logistic function is the other one that is always going up. So here are the 6 functions that do nothing but go up. Perfect. Okay? All right, so you got a job to do, right? What's your job? Make flashcards and bring them for a grade the next time we have class. I don't care what they're